Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm happy today to be able to announce that Fabio Massimo Zanzotto is visiting from the, let's see if I can get this right, the University of Rome, Tor Vergata.
Correct.
Very good, okay, which is the most prestigious University of Rome, as I understand it, although there are other pretenders to that throne. Fabio is an associate professor there, and he works primarily on problems such as extracting knowledge from text and robust parsing. Today he's going to be talking to us about an issue that has been increasingly important in the field recently, which is this task of textual entailment, which has a lot of excitement, I think, and is now, we were just looking, is now being taken over by NIST and has 40 different groups participating this year in this year's conference. So it's a growth field. And I know Fabio through the Recognizing Textual Entailment workshops, that the predecessors of what is now the NIST evaluation, where he's been a reliable participant with exciting results always. So I'll be curious to hear what he has to say about learning rules. Heuristic rules? No. No. Machine learned rules for recognizing textual entailment. Take it, Fabio.
Thank you. So the work I'm presenting now is a joint work with Marco Pennacchiotti and Alessandro Moschetti from that now are one in the University of Trento and the other one in Saarbrücken in Germany. So let's start with just a few words on the task, but I don't think they are necessary. The problem in recognizing textual entailment is given two pairs of sentences, the text and the hypothesis, T and H, determine whether or not T implies H. This is the basic problem. So if we see this basic problem as it is, in this simple way, we can imagine that it can be seen as a classification task. So you have to say yes or no to this problem, to this pair of sentences. So if it's a classification task, we can try to learn a classifier from annotated examples. But the real problem in this case is trying to understand what is the best feature space to model this problem in. This is the real point. It's not a matter of finding the best algorithm, but trying to understand, to figure out what is the best feature space where to model this pair of sentences. If we go around, we can see that there are many possibilities, basically three. One is a set of possibilities that we can call the distance features that describe the distance between T and H. The second one we can call entailment trigger features. We know that something is giving a possibility of entailing T, of entailing H between, starting from T, and then we model that as a feature. And the other one, the one we have be interested in, is trying to model the content of both T and H, and we call these pair features. And we can go. This is a dimension of the classification, and the other dimension is which is the representation that you use. It can be bag of word, it can be a syntactic representation, or it can scale up to a semantic representation. So let's go quickly in this kind of features of different features. In the distance features, we can see, for instance, the number of words that are in common between T and H. So the more are common, there are common words between T and H, the highest is the possibility you have that T implies H, or things like that. Or you can see the longest common subsequence, or the longest common syntactic subtree between again T and H, and that's why we can call them distance features. On the other hand, we can use these entailment triggers that can capture polarity. For instance, one sentence has a negation, is a negation on the other sentence, or antonymy. One sentence has one word that is an antonymous of the other sentence. And so you can collect all these kind of features. Another place is this one. Instead of modeling the distances between T and H, you can model the content of T and the content of H. In a bag of words style, you can have and, ears, solid that appears in the text, and ear, solid that appears in the hypothesis. And those have two different feature sets, two different bag of words sets. Or you can use syntactic trees for the first part, for the text, the syntactic trees for the hypothesis. Let's see what we can learn from here. Apparently, we can learn very stupid things. That means that T implies H when T contains AND. So it doesn't seem to be very relevant. Or on the contrary, T does not imply H when H contains AND. That is because you can treat them separately in this way. So you don't have a distance between T and H. You are just modeling the content of T and the content of H. That's the basic distance. So just to make it clear, it seems to be totally irrelevant, this space. But in fact, this is the space we have investigated. So in the rest of the talk, I have to convince you that this is a good space to investigate for that problem, for that kind of problem. Many approaches, if we go to the 2 dimensions I gave you, many approaches are here in the bag of word in the distance feature, using the distance features in a bag of word fashion or in a syntactic way. Someone are using entailment triggers. And when they use entailment triggers, they go basically to a semantic representation. For instance, they use the modality of the verbs or things like those. And we tried to investigate this pair feature space. And we focused, yes?
You may mention later, but I'm just curious. If you have 3 different representations, for each representation you can extract different set of features. And if you want to train a model based on the features, do you think it's better to train a single model which contains all the features extracted from different representations, or just train 3 different models, each for one particular representation, and then combine these models?
It's maybe I can answer later on that question. But just to say, it's maybe better to use a different feature space and combine them with a kernel function in a single classifier. We didn't try to use many classifiers for each different feature space for the moment. And so we are investigating for the very first work, we have been investigating the syntactic feature space within the pair idea. That means trying to model the text, the content of the text, and the content of the hypothesis. So in the rest of the talk, I have to describe you the initial idea. That means why we were interested in this strange feature space that apparently gives us not so relevant information and focus the algorithms on not so relevant information. And then I will give you the 2 different research lines we are following. One is the representational issues, that is trying to move from syntax to something more, to semantics or something that is taking into consideration something else. And the other one is the computational efficiency issue, because these algorithms will be very complex, as you will see. So The initial idea is this one. Try to put the idea of placeholders in the pair feature space. Why? Because what we want to do is we want to try to discover rules to discover, or better, exploit rules like those that says that you can have a movement from the MP that is object to the MP that is subject if you lose this NP. This is the basic idea. And in this example, it works. Then you can say something that I will tackle afterwards So if we have examples like those in the training examples, then we can apply these to other examples that are the examples to be classified. For instance, in these examples, we have the cow that have eaten animal extract, and we can apply the same rule because farmers fed cows with animal extract. So we can somehow apply a similar rule. So those are the things we want to do. How do we try to do that? Trying to model this pair feature space, including this kind of placeholders that are acting as variables, in fact. And we want to learn or exploit these rewrite rules that are written in the examples. The fact that you can move you can move bits of sentences from the text to the hypothesis, and keep the fact that you have the implication in place, or the non-implication in place, depending on the example. What we are trying to use is we are trying to model this space in an implicit way using a kernel function, a distance between the examples, instead of exploring or exploding the whole space. So what we need is only to determine the distance between examples and not determining how the examples explodes in features. So,
whenever I look at alternations like this, I am struck by how much like translation this is. I mean, you do see alternations like this across language pairs. And always I'm thinking of these RTE algorithms in terms of what's already been done in translation. And you're doing a special case. You're creating a special case algorithm here for something that I think maybe isn't adequately dealt with in the translation space right now, but does it make sense to do a special case algorithm for the monolingual case, or should this be whatever machinery is being done in the machine translation space? I mean, is it any different in character from what needs to be done or has been done in translation?
Apparently not, because the only thing you need is for this syntactic feature space is to have the syntax in place for both languages and the relations between text and hypothesis, that is target language and source language, with respect to the words. The real point is, I believe, that in translation it's difficult to have the syntax. I believe, but I'm not sure. I'm not an expert.
I don't want to argue that it works well, but at least people do try to model this kind of alternation, right?
It falls apart fast if you have syntax on both the source and the target.
Okay, right.
Where that's not a problem when it's all in English.
Okay.
You get matching transcriptions.
So here, to be exact, the VP1 should not be labeled VP1 on the right-hand tree because it's a different verb. Right? Because on the T,
Yes, but they are related verbs
how do we know if they're related?
by wordnet or
Well,
things like
suppose
those.
related.
Wordnet?
Yes, eaten and fed. I choose this example because then I have to tell you that this is not a correct rule to learn. right? But it's the next part of the talk. I'm just using this example because then afterwards I will tell you, okay, we need something more to solve it. Okay, so I just go back to that slide, and now the real problem is try to introduce these placeholders that in fact are acting as variables relating things together, relating the text and the hypothesis. So let's try to imagine to have just one pair here. The idea is to try to label those things with a number that represent the relation between the two things, between text and the hypothesis. Then what else we can do? We can make the numbers climb up with the according to the head of the constituent, and then we have this nice representation.
How do we produce the map?
The mapping between in this case we are just looking to the lexical, to the word.
The same word.
For that, but we can use many things. For instance,
No word alignment algorithm involved.
not for the moment, because we have quite similar sentences. And we use also WordNet, the lexical distance.
It's kind of rule-based alignment, lexicon-based alignment.
Lexicon-based alignment.
That's a function of the task to some strong degree,
Yeah.
right? Because the task involves sentence pairs that are often very similar in terms of length.
So the real problem is that whenever we tag with the same numbers, here I use letters, another examples, we cannot be sure that we can compare these three with the other three over there. Because numbers and letters here, just to make the difference very clear, have different meaning, are relating different things. So even if these two are sharing this rule, we cannot discover that this rule is exactly the one that is shared between the two examples, because we have different names in the labels. That is, 2 is not related to A. We need then to find the best, first of all, the best correspondence between the two sets of placeholders, the one that is related to the first TNH and the second one that is related to the second TNH, and then map trees, find the similarity between the trees. So this is the real problem, adding placeholders that are acting as variable. So the computation is done like that. We have this set of correspondences, that is the correspondences between the placeholders of one pair with respect to the correspondence of the other pair, or with respect to the placeholders of the other pair, and then we apply this changing of the correspondence of the placeholders on the tree we have. Okay, this is the equation. Let's go with an example. Maybe it's better. I can explain myself better. Here we have now we consider only one tree because it's the same problem, and we have there the set of correspondences between the placeholder of one pair and the placeholder of the other pair here. So you have here the fact that in the first correspondence set, A is related to 1. The first activity we need to do is selecting one of the correspondence set and changing. That means that this A is related to 1, B is related to 2, and C is related to 3, and then translating using the transformation T that applies in the same label the corresponding label. So we have now A1 because is what the correspondence is saying to us. And the same happens for this second one. So now we have comparable tags within the two trees, and we can compute the similarity between these two trees with an algorithm with a similarity function that computes similarity between trees. So now the problem is reduced to tree similarity comparison. Once done that, it has been done, we go to the second correspondence set that changes one arc there. D now is related to 3, and we apply the second correspondence set to the pair, and what we obtain is changing D now is related to 3, and so with this new tag, again, the two trees are comparable, because now we are sure that the relational information has been used correctly. And we can compute again KT, that is the distance between this tree and this other tree. How many subtrees are in common between this tree and this other tree. So we are capturing somehow the relations that we have between the text and the hypothesis, using also this relational information. So as you can imagine, this is very complex because it depends on how big is the set C of correspondences. And this is combinatorial. So we need to keep C very small. To keep C very small, the first thing we try to reduce the number of placeholders, giving the same name to the placeholders that are in the same small constituent that has been called chunk times ago. And we can also focus only on the relevant part of the text that is related to the hypothesis, not on all the text. And in this way, we can control complexity. So here we can have some result. The data set used for these experiments was the RT1 and RT2. And then for the syntactic part, we used the Charniak parser. For detecting the relations between words, we use WordNet, and WordNet similarity package to detect also the similarity between words, to link the text words with the hypothesis words. We used also inverse document frequency to lower some words, and SVM Lite for coding the kernel function. The results we had are those. As you can see, here are the different data sets. They're what we used to detect the relations between T and H, between the words of T and the word of H. We used the token or lemma similarity, if they are the same token, if they match. The ing and correct distance, if they are the relationally related forms. Then we say that entailed verbs taken from WordNet were related. And we use also the edit distance to match words that are kind of similar but not equal. And the IDF to reduce the importance of some relations. So the first thing, this means that the syntactic tree with placeholders have been used, and the other ones means that we used only the syntactic trees in order to see if the placeholders are useful or not in the overall process. What he had is that, first of all, just using token and lemma for RT1, we had 53.88, but a very interesting point, sorry, until here is only a space with one feature, that is the distance between T and H. There, after that, the last two columns are spaces in which there are pair feature spaces in which there are only syntax or syntax with placeholders. The last one is syntax with placeholders.
What does only syntax look like?
Only syntax means that we have these trees without these additional labels. I go back again. Okay, these trees without additional labels.
So there's no relation between the trees.
There's no relations between T and H.
Okay, so it's just
We want to see if this adding complexity, that means adding the relation between T and H, is somehow useful. So we have to compare with the model without adding the complexity. Okay, let's go to the result again. So the first thing to notice is that within the lexical, using only distance, the distance space, a big impact has been given by using the IDF. So just using the IDF for the first development and training set, results increase a lot. And this is disappointing somehow. Because since maybe someone of you knows, but not everybody, in the training and testing set of RTE, we have 50% of positive and 50% of negative examples. So we would expect that the baseline should be around 50. This would be a nice task if it's like that. Instead, somehow the baseline goes until 59% in the first one. So what we discover here is that we have a kind of improvement between using our method with respect to the baseline, that is 58% somehow. And instead, we have also an improvement with respect to the basic, to the syntactic space, to the syntactic feature space. So adding placeholders seems to help. Moreover, it seems to help more in this area, that is, we randomly split the training and the overall set of RT1 in two halves. So it seems to be more useful. I mean, it seems to be that the division has some strange behavior. But generally, what we have is that we have a big increasing when we randomly split training and testing. Okay, so this ends the first part of the talk, and then we go to the open research lines that we have now. The first one is the representational issues. We try to put on this model that we have now some more information that comes from semantics, or comes from the kind of the relations that words have. On the other one, since the algorithm to compute the similarity I've said is exponential, we need to find something better because exponential is not always the best thing to do. So let's go for the first one. The first idea we had, and let's say is for the moment the only idea that was successful, because we tried many things, but the only one that was successful was that, is to try to introduce really shallow semantics features in this space. And we introduced that using the typed anchors, typing the anchors that are the relations between T and H. Let's go how it works. We had this initial idea, that is the initial examples, that apparently doesn't work. In fact, here we have a verb VB1, that is somehow related to the verb VB1 here, but they are not the same verb. In this case, died is somehow caused by killed. The previous algorithm, the previous idea, doesn't take into consideration that. So it comes out with comes out with very strange rules that are used. In fact, if we use this rule on this testing example here now, this rule fires, but it's not correct, because in this case we have words that is related to declared, and we have these migrant medicine makers that declare something, and the other sentence is FDA warns migrant medicine makers. So the first one does not entail the second. Even if this rule, if we link words with declare with some lexical similarity, would say, this rule would say, okay, this is an example of implication, but it's not. So what we need to do is try to build better rules. And in order to build better rules, what we need is to try to encode the information on the feature space we are using. That is this feature space of text of fragments, of 3 fragments. So a better rule would be trying to relate these 2 verbs with the relation they have. In this case, this is a more reasonable rule with respect to the one that links these 2 verbs with the general similarity relation. So if we have a cause relation, apparently the movement of the object that becomes the subject is more reasonable than in the other case. So we need to encode this information within the rule. The first way is to try to encode these as an additional features to the nodes. And again, this is not a solution, because if we don't propagate it, what we have is, again, we will have rules like those. So we need to propagate it. Let's see how to propagate it. It's not very simple. We cannot propagate it using the head of the constituent, because again, we will have a rule that is not useful. In fact, what we need is to try to propagate according to the relevance of the type. That means, in this case, this relation is somehow more important than the fact that the other part is equal. In this case, we have a tall with respect to short. So we need to climb up the tall part. And now we are learning, we should finally learn the correct rule. Because in that case, this is not implying the other one. I missed to explain the example. In this case, the example was John is a tall boy with respect to John is a short boy. So, in fact, this does not entail the other one. And we need the mean to discover this fact, that this part is not entailed by the other one. And apparently, the idea is to type the anchors, this anchor that is saying the John is related to John, is an equal anchor. The two things are the same. Instead, this one, tall with respect to short, is a antonymy anchor. So we model the antonymy using this symbol, but it's just a symbol. And what we need now is to make the antonymy clean up and not the equal. Because if we make the equal clean up, this is what we can learn. That is, again, a wrong rule. So, let's go to the experimental evaluation. We used, again, one data set that is RT2 and a random split of RT3. RT3 0 and RT3 1, D1 and D0. And we use three kernel functions. One is the one that I presented at the beginning. Now is the syntactic trees with placeholders. This one is the shallow semantic trees containing also the type of the anchor. And the other one is the lexical distance that is always the best baseline that we have. And those are the type of anchors we used: the antonymy, the part of, the verb entailment, the similarity, and the surface matching. This is what we had using only the tree, that is the tree with placeholders. We increase something using the TAP model, that is this model with typed anchor propagated. And this is also here when we use the lexical features plus the TAP model. You see here we can increase something, but unfortunately we have the same level of the lexical, because this is for RT3, the lexical model is giving a very high baselines. This is a real problem.
Is this really any different though from just taking a word-based model and assigning some cost to any mismatch that you can find in an anatomy resource?
Yeah.
I mean, if you just, at least with this example, it just seems like it's all the machinery buying you more than you would find if you just associated a cost with picking.
Yeah, sure. This is an approximation of the problem, an approximation of this. I mean, you can approximate, but then you can lose. You don't know where these antonymy are. Where these antonymy words are. In this case, you should also capture the fact that there is a movement from one place to the other. And for the antonymy, maybe is relevant for the antonymy with respect to verbs. If one goes up and the other goes down.
But isn't that the relevant baseline? And isn't that really what you should be measuring against? Just a keyword-based version? Oh, that is there. Okay.
This is the lexical.
That doesn't factor in the mismatch, does it?
Well, that would be an even
Yes,
higher
That's what I
baseline.
mean. That's what I mean. But that higher baseline is the right one, isn't it? Where you
You
are
want
ignoring
to-
the contribution of syntax and just saying this is the lexical baseline where I'm allowing some fuzz on individual lexical items, even to the extent of assigning a cost to antonyms or scalar adjectives that are
Exactly.
not.
So in that case, you are mixing up two spaces that I've given at the beginning. The one space is the distance space, and the other one is the entailment trigger space. You can put another this relation you are saying, or in a cost, as you want, or as a feature. This feature is active. And then, yes, we can compare also against that.
Don't you need to do that to isolate the value of the syntax?
No, because the value of the syntax has been already, let's say, investigated with the other experiments. So now I'm trying to make more complex the model of the of syntax, and we have the machinery that can model these things both in the tree or in the entailment trigger feature space, because we can combine also these different feature space. We have the distance feature space, the entailment trigger feature space, and the pair feature space. And we can combine everything together. So yes, this is a valuable comment that I will try to see. But as you see, when you put lexical distance, if you have these high baselines, you are not understanding if in fact what you're putting more is giving you a result. Because these, for RT3, these are really too high for this kind of task. They should be around 50%, because there should be complex cases for other algorithms. That means algorithms based only on lexical distance. That's the problem. You should have around 52, 53, but not 70. Okay. The computational efficiency issue, if I have still time, yeah, is instead this one. Let's try to observe closer the computation of the kernel function we proposed. In this case, this one was the second correspondence set. If we concentrate also on the first correspondence sets, we see that there is a lot of the part of the tree that is in common between the first correspondence set, that is this one, and the second correspondence set, that is this one. So at least we cannot solve the exponential complexity, but at least we can use again this in the dynamic algorithm in order to reduce the effective computation, the computation that goes on. We are not reducing the complexity. We are just writing a better dynamic algorithm. So during the computation of KS, the idea is that many subparts of the trees have been already computed. So we try to use this to improve the real computation of the kernel function. So how to do? First of all, how to explain that? First of all, I try to explain better how the similarity between two trees has been computed, because I need to include the set of correspondences between in the trees during the computation of the similarity between trees. And then I will try to say how we try to reuse the computation already done in KS, and then some experiments. Many of you are familiar with this, but I go through quickly. The idea of having these trees, this subset of trees, is the fact that you will have a feature space in which all the tree fragments are represented. So the idea is that from these delivered talks, all these three fragments are the features that are active from that fragment of tree. Then if you see the feature set with the point, the vector that represents the levers at talk within the feature space, this will be the vector having 1 in specific places that are the places where that are representing the subtree that is relevant. And then if you have 2 of these examples in the sample space, the combination of them counts the number of subtrees in common. the product of them. So the model that has been proposed to count without explicitating all these trees has been this, using this delta matrix that then has been summed up with respect to the nodes of the first tree and the nodes of the second tree. This delta matrix is 0 if the productions coming from the first from the node you are observing are different from the node you are observing in one tree and the node you are observing in the other tree. Is 1 if they are preterminals and they are equals, and instead, and this come here is the very interesting part, you can compute the similarity between a tree starting from nx and a tree starting from nz by using its child lists. So if they have the same child list, the number of trees that they have in common is given by this production. So now the idea is to try to include the correspondences, the relations between the placeholders in this delta matrix. Then we need to translate the fact that we have some repeated computations, and then we try to redesign the overall computation to exploit the property of step 2. The first thing is that we say that KS is trying to maximize the similarity between trees across the correspondences. So we can see this also as this function here that puts together P1, P2, and C in a unique function. And in this case, this C can be replicated also here in the delta matrix. This just changing symbols. It's nothing more for the moment. But what gives us? It gives us the possibility of restating everything with respect to the existence of this C. Now, nx and nz gives 0 if the productions of t and x after the changing given by C, the correspondence C, is equal or is not equal to the t and z after the production C, the changing C. If you remember, the t and x C is the function that changes the placeholders from one name to the other name. So this is similar to the other one, just having in mind that this is relevant. And this, again, is similar to the other one. All right. So now we need to try to understand how this how to reuse the previous computation. If we focus only on that, the two correspondence set here that we have, A1, A that goes in 1, B that goes in 2, and this C that goes in 3. Let's see, if we just act on this sub-part of the tree here, the only relevant part of the correspondence sets is the one in green, because here C in this sub-tree doesn't appear. So what we need, focusing on in here, is just to know what is the sub-part of the correspondence set that is all this, that is active in this sub-part of the tree. If we have two different correspondence sets, they will give the same changing to this part of the tree. So this is the idea, just finding the sub-part that is relevant. And we call this subpart the placeholders that are the PN, that are the placeholders that are containing in the subtree starting from n. So the variables that are effective in that part of the subtree. And we can say that C projected on A and B is the projection of the correspondence set, with respect to this. So the property that we used before is this one, that NC, this delta is equal to this delta, that is equal to this delta, if the part that is, if we have if we have a correspondence set projected on only the active placeholders in the subtrees are equal to the other one. So if we have C1 and C2 for the only part that is relevant, equal. I've been not so clear. So just going back, if we have this subpart of the tree that is the one we are interested in, this transformation and this transformation are the same, exactly the same, because in this subpart of the tree, only A and B are mentioned. So the two transformations are the same. The idea is then here, we just need to put the projection of the correspondence set and have a look on how it's nice. This is the number of delta iteration, how many times we compute the delta. And this is the percentage of training data. So, as you see, this is still very high. Instead, the number of delta computation here becomes very low. So we gained in time. We didn't gain in complexity, because the complexity is still, I see your face that I'm not so clear.
What is the cause of the exponential complexity here? Because certainly that similarity kernel is polynomial, isn't it?
No.
Like the Collins kernel that you started with.
Yeah, but not this.
Is it because you're iterating over a bunch of different placeholders? That's the complexity right there. Okay.
That's the set C is combinatorial, so it's exponential. And that's the real problem for the moment. So yes, the kernel we are starting with is a polynomial with degree 2, but in fact the maximization that we are doing is not polynomial. So the nice thing seems to be, even if we didn't reduce the complexity to a polynomial complexity for the moment, we still have a nice reduction in computational cost. And just to go back to the summing up, the idea has been trying to learn syntactic rewrite rules from examples, and the basic point was trying to introduce these placeholders that acts as variables. Then we started two different research lines that are, one, it seems to be normal that adding more semantics should help in this kind of task. So why don't we add semantics? We tried many things. For the moment, the only one that seems promising is this one, trying to model these novel relations between the text and the hypothesis using typing anchors, typing these placeholders. And then the second research line that is still active because we didn't solve the problem completely is this one of the trying to reduce the computational cost of this. So we need really to try to see if there are models that are in fact polynomial and not exponential. Here's some reference if you want to have some better idea on that. And I concluded.
More questions, or did we take care of them all?
So just going to what Bill said about the line between this and translation seems very fine. And you're doing basically a tree alignment to an extent is what you're performing when you're trying to find these correspondencies or placeholders. So if you are looking for a solution to the complexity problem, there are people who have studied this on a formal level. There's keywords you might want to look at are things like tree substitution grammars. Jason Eisner's and Giorgio Sada, I think, both looked at these sorts of ideas somewhere.
Jason Eisner and
Not together, but Sada, I don't know how to pronounce his own first name.
George.
So these sorts of people might have looked at problems like that. If you're going to keep arbitrary number of branches, like numbers of children, then you're probably not going to be able to get the complexity down. But if you're willing to binarize before you do some of your comparisons, you might be a shot at it using some of these synchronous parsing formalisms.
Yes, thank you for the suggestion. I have some initial, some other idea on how to put this complexity N4, but it's still N4. That is much.
Because now you're treating the lexical distance space as your baseline. What if you did the triggers? What is the performance of only the triggers?
Very low. Because what we saw was very low. We model only the triggers that are shown in one slide, in the third slide. It doesn't cover many examples. That's the problem. So you need to combine it with something else.
And you haven't yet combined lexical distance with
Yeah, it goes down. It
with
goes
the trigger.
down.
That's the part that surprised me. Why should it go down?
I really don't know. I mean,
did you look at any of the examples?
apparently, okay, it doesn't go down completely. It just is unaffected, statistically unaffected. It means it goes up a little bit, and then maybe if you do cross-validation, it goes up and down, so statistically it's irrelevant. That's the problem. Because there are not too many examples. So you don't know if they are in the training or in the testing when you mix everything up. So it's not. What we are trying to do is also not using only the fact that these two things are in antonymy. So there are words in antonymies. We are just also trying to replicate some rules that we have in mind should work. For instance, the fact that when you have a cause relation, you can use between two verbs. You can say this implies that using the rules I've shown you, and that if it's active, then it gives you 1 on that feature. The feature is active. So we tried many things. The only problem seems that whenever you add something, it goes down. Because what you add generally is affected by the problem of ambiguity. You are not sure you are adding something that is correct. The only disambiguation we are doing is the fact that, let's take an antonymy relation, is the fact that the antonymy holds between the text and the hypothesis. This is a way of disambiguating, because even if the word has several meanings, you take only the meaning related to the fact that you are looking it into a context, but we are not doing a real world sense disambiguation. We are just doing this disambiguation because the two words appear in the same context. So maybe this can be the problem. Apparently, as you add more layers, interpretation layers, what happens is that you add noise instead of adding. This is what it seems to me at the moment.
So is part of your, because you're pointing out that the baseline for lexical distance is so high, is that a criticism of the way that RTE data
No,
samples?
absolutely, yes.
Because I mean, your first slide where you did the comparison of all the systems, where on RTE1 the syntactic patterns were buying you quite a bit. The increase that syntactic patterns showed was quite large, and then on RTE2 less. That's a reflection of the way RTE1 was constructed, where it was constructed with a lot of syntactic variation, and so you validate that with your experiments. But so I wonder how much of what you're finding, the fact that if you actually reduce, the more features you try to add, it actually drops your accuracy. Is that a function of how the data set is created, or is it a function of the actual problem?
I believe it's a function of how the data set is created. But I really would like to see if there is, this year there will be a three-way classification. But if it was a two-way classification, I would like to see that the lexical models behaves around 50%. Because in that case, you are tackling the complex cases. Otherwise, the lexical model is already the one that every information retrieval system is using. So if you're using that model to pick up the sentences you want to see if they are somehow related or not to your text, you need to see the complex cases, not the one that can be already solved by the lexical models. Otherwise, it's somehow useless.
Thanks.
Thank you.